Okay, so what we're going to be doing here, guys, with today, the first half of it's going to be pretty much review. It's stuff we've been doing already with reactions, that is balancing. Okay, we're just going to kind of go over that. This is your formal notes on it, even though you already know kind of how to do it. And then we're going to look at, all right, now if I'm only given the reactants of a chemical reaction, can I predict the products? All right, that's what we're going to start today. We'll work on it again tomorrow. We'll start our pre-lab activities about halfway through class, or 3/4 of the way through class tomorrow. We're in the lab on Wednesday. Okay, Thursday we'll be doing more stuff on prediction, and then we'll see where we are on Friday. If we're really getting this prediction stuff, we might be moving on to the mole equation by Friday. So that means that probably by Thursday of this week, I'll have an idea of when our unit exam will be. All right, and I will let you know that date at some point during this week. Okay, everybody with me there? So that's what's coming up, okay, for this week. So, key points for today is stuff about something you took last year, which is the law of conservation of mass. Sometimes that's called the law of conservation of matter, okay? Tomato, tomato, okay? It doesn't really matter which way you say it. The idea is the same. You can't create anything, you can't destroy it, okay? So if we're talking about atoms on one side of a reaction, there have to be the same number of atoms on the other side. That's why we do all that balancing with our chemical reactions. Okay, so we need to understand that the amount of atoms on the reactant side of an equation must be the same as that on the product side. We've got to use coefficients to balance. You guys have already been doing that. Okay, and understand that matter cannot be created or destroyed. That is essentially the law of conservation of mass. Questions there? Okay. Okay, so mass has to be conserved in reactions because we can't create or destroy anything. So if we're looking at this reaction here, which is what kind of a reaction? It's a synthesis reaction. Two elements are reacting to form a single compound. Okay, so we've got two molecules of hydrogen containing how many hydrogen atoms? There's two molecules containing 4, right? Sorry, each molecule has 2. That's what you were thinking, Shay. Okay, so we got 4 hydrogen atoms in total reacting with 1 molecule of oxygen, which has 2 atoms of oxygen. And then on this side, we've got 2 molecules of water. Okay, and these 2 Mickey Mouse looking molecules, okay, have got 4 hydrogens and 2 oxygens between them. All right, so we have the same amount of matter on both sides, right? And that's what has to happen. Okay, is it possible that if I had more oxygen than I needed for this reaction to go, that I would have extra oxygen over here? Yeah, sometimes in a reaction, in fact, most of the time in a reaction, at least one of the reactants is in excess, which means there's more of it than is needed. So it doesn't react. It's essentially left over. Right? In a proper reaction, you would actually write the leftovers on the product side. We don't have to worry about that so much in Science 10, but it's important to know that no reaction is ever this perfectly clean, where, ooh, I got exactly the right amount of atoms for this reaction, and they all reacted and they all paired up, because in reality, that never happens. Okay? For example, in a campfire, okay, if you got a campfire burning, do you use up all the oxygen in the area? No. I mean, there's always oxygen left over, okay? But we just don't really take it into account, right? Okay, so since all matter has mass, the mass of the reactants must equal the mass of the products. And if we used to do a lab on this in Science 10, we just kind of started running out of time as more stuff got in there, where we would actually contain the gases from a reaction in a balloon. We would have like a flask, okay, with a test tube inside that contained one reactant, and then there was another reactant in the flask, and then we would put a balloon over the top, turn it upside down so that the stuff would come out of the test tube and react, okay? And then as it reacted, a gas was formed and the balloon would catch it, right? What we would do is take the mass before and take the mass after. Since the balloon catches all the gas doesn't escape, right? Was the mass the same before and after for us every time? Yeah, it was. Okay, if nothing's allowed to escape, then you never have any worries. Right? Sometimes it looks like the mass isn't conserved. If a gas is formed and it isn't captured, then it escapes, and then it looks like you suddenly have less mass than you started with, even though that mass is still out there. Okay, it just wasn't captured, and then as a result, not measured either. Right? So it's always important to make sure if you're testing this that you've got a sealed container in which to do it. Okay, now, why would we use a balloon and not just a rubber stopper? Pressure. Yep. Okay, we tried it a couple times with a rubber stopper, and we always lost the gas, because either the rubber stopper would pop off, which was not as bad as the other situation, but oftentimes resulted in splatter, okay, and people would get it on themselves and on their lab aprons and goggles. Hopefully they were wearing those, okay. But what was worse is sometimes they would hold the stopper on, shake this thing up, and the bottom of the flask would break, okay. Like it would actually create enough pressure to shatter the glass, okay, and the bottom of the beaker would just come flying off, okay. So yeah, gases can exert pressure if you contain them in a fixed volume. All right, and that's one of the problems with chemical reactions, okay, is that sometimes the stuff that's formed, it's not that there's more of it, it's that it takes up more space, okay, and that can create problems with pressure. All right, so law of conservation of mass. In any physical or chemical change, the total mass of the starting materials must equal the total mass of the product materials. So probably underline that. That's something that could be like a multiple choice kind of a question, strictly the definition of the law of conservation of mass. Okay, which one of these rectangles along the bottom, so A is the reactants, okay, these are the products. Which one of these, B, C, or D, shows the law of conservation of mass being obeyed? D. Okay, I mean, we've got, on this top one here, we've got 8 yellow spheres, okay, or 8 yellow atoms, right? 8 yellow atoms up there, okay? There's definitely not 8 in here. There's definitely not 8 in here, but there's definitely 8 in here, okay? You only really need to look at one of them to know whether the law of conservation of mass has been obeyed. If there's less than what you started with, you know it didn't work. Okay, everyone follow me on that? Okay. So when you're balancing a chemical reaction, we've kind of talked about these steps, but at least now you kind of have them in your notes. Okay. The first thing is that you write the chemical formula for each reactant, and if you have them, the products. Okay, including the state of matter. You don't have to write that. Take that off. You don't have to write the state of matter. Okay. Step 2, try balancing the atom or ion present in the greatest number. Okay, and we've always said that that's how you do the balancing. You start with whatever's present in the greatest number and go with that. Okay, unless that thing is which atom? No, oxygen. Okay, oxygen just tends to mess everything up if you start with it. Okay, we kind of tend to leave oxygen for the end. Okay, and we use coefficients. That's numbers in front of the element or compound to get equal numbers. Remember, we said that we can't change these small numbers. Okay, I can't just go, oh, I suddenly need 4 carbons, so I'm going to put a 4 here, because does that change the material? It does. Okay, so we can't do that. All we can do is change the big numbers. Okay, that would go in front of that molecule. Say I have more of it. Okay, so we got to remember that. That's how we balance, not by changing the molecules themselves. Okay, step 3, repeat step 2 to balance each of the remaining atoms or ions. And then step 4, double check. Okay, sometimes when you balance that last thing, it throws something else out of balance. Not very often. We've seen that most of the time when we're really done balancing that we know, okay, because our last thing balances something else. All right, so it's just always a good idea, though, to double check and make sure. Hey, questions on that stuff? All right, so that's all review, right? We know how to do our balancing stuff. All right, so copper wire is immersed in a solution of silver nitrate. A single replacement reaction occurs. Okay, so if we're looking at this reaction here, okay, what should I balance first? What's present in the largest number? Nitrate. Nitrate. Okay, we want to balance nitrate. It's got a 2 beside it. It says here oxygen atoms are present in the greatest number, but they're part of nitrate, so we're going to balance nitrate first. Okay, so there's 2 nitrates over here, so what do I need to put in front of the silver nitrate? 2. Okay, so if we do that, now we've got nitrate balanced. Okay, there's a 1 in front of copper nitrate, there's a 2 in front of silver nitrate. Okay, now that gives me 2 silvers, so what do I have to do here? Put a 2 there, all right? So I put a 2 there, and there's already a 1 in front of that. Okay, so then we're done. Okay, ringing a bell for everybody? Okay, big reminder here. Polyatomic ions are balanced as a single unit, not as individual atoms. Exception for that. unless they decompose. Once in a while, a polyatomic ion will actually break up, okay, in a reaction. Not in the 5 basic types that we've gone over, but once in a while, okay, a polyatomic ion will actually split during a chemical reaction, and then you can't obviously balance it as a single unit. All right, so I want to look at a little bit of predicting now. Okay, so this is what a question that is asking you to predict a reaction will look like. You will only have the reactants. Okay, now, are the reactants different for each of the 5 types that we've gone over? Right? No 2 of those 5 reactions starts the same way. Right? If I have 2 elements reacting, it's what kind of a reaction? Synthesis. Okay? If I have a single compound as my reactant, I only have decomposition. Okay? If I have a carbon-hydrogen containing molecule reacting with oxygen, I have a combustion reaction. Okay? If I have an ionic compound and an element, I have single replacement. 2 ionic compounds, double replacement. So we can tell what kind of reaction is going on just from the reactants. Okay? And it's important for us to be able to do that. Okay? That's why I had you identifying all those reaction types on the worksheets that you did before when we were working on full reactions. Now we've got to be able to identify just from the reactants. So in number 1, I've got calcium reacting with oxygen, element reacting with element. So this is a synthesis reaction. What happens in the synthesis reaction? They go together to form one compound. All right, so that means I've got to do this. Ca goes with O. Now, what kind of compound is that? It's an ionic compound. So what do I have to do with ionic compounds? I have to drop and swap. Okay, this one's a 2+, this one's a 2-. So yeah, that one's okay. Right? It's balanced off already. Now what do I do? Is my reaction balanced? No, that's what I do next. Last step is always to balance the reaction. Okay, I've predicted my products, which wasn't very hard. Okay, now I've just got to balance the whole reaction. Okay, calcium's already balanced, so I've got to go to oxygen. A 2 there will balance my oxygens, but it gives me 2 calcium, so what needs to go here? Right, and that's it. Okay, so it's not too terrible tough. All right, number 2, I have a single compound. What kind of reaction is that? Decomposition. So it's going to break up into its 2 elements. So we're going to have magnesium over here and sulfur. So some things I've got to be aware of when I have elements by themselves. Are some elements special? Is sulfur one of them? Is magnesium? No. Okay, so magnesium is going to stay as just magnesium, but sulfur is going to need a what? An 8. Okay, that's one of the things we always have to check. When we're predicting products, these are the things we have to keep in mind. I got to swap and drop ionic compounds, and I got to look for special elements if I have them. Okay, so now I've got a balance. We start with the thing in the largest number. That would be sulfur. So what do I need to put here? Okay, and how many magnesium does that give me? 8. Right? Not too tough, right? Okay. Next reaction, carbon-hydrogen reacting with oxygen. Combustion. What are the products of a combustion reaction always? CO2. Water and CO2. Okay? Always. Okay? Those are always the products. Combustion reactions are the easiest ones to predict because it's always the same. Doesn't matter what you got over here, it's always going to be CO2 and water. All right. The special balancing rules are balance alphabetically and the rule of 2. Do we need to apply them both for this one? No. 3 is an odd number. Okay? I only apply the rule of 2 if I have an even number of carbons. So, let's balance the carbons. There's 3 over there. Balance the hydrogens. There's 8 here. Now there's 8 over there. And now I balance my oxygens. 3 times 2 is 6, plus 4 more is 10. 5 times 2 is 10. Okay? The combustion reactions are probably the easiest ones for prediction. Okay, for number 4, I've got hydrogen chloride and sodium hydroxide. Those are both what kind of compounds? Okay, so this is a double replacement reaction. In a double replacement reaction, we swap the what? Right, which are usually metals. Okay, we swap the metals. All right, so essentially we're just going to do this. Sodium's going to end up with chlorine, hydrogen's going to end up with hydroxide, and we are going to have okay, this is a strong acid reacting with a strong base, and whenever you have that, you get water and a salt. Happens every time. Okay, that way it neutralizes, okay, whatever it was you had before. Okay, now I've got to balance. Were there any little numbers? No. If there's no little numbers, it's already balanced. Okay, everything's a 1, so we should put 1s beside it all, just so there's no confusion. Okay? All right, I'm going to write one up here. I want you guys to try it. Okay. Okay, give you a minute or two on that one. Okay, what kind of reaction is that one? Single replacement. Okay, we have an element and it's reacting with an ionic compound. Single replacement reactions are probably the toughest ones for prediction because there's the most things to remember and the most things that can happen. All right. By the most things that can happen, I mean this. Are you going to get an ionic compound formed in the products? Yes. Will you have to swap and drop that? Yes. Is there a chance you could get one of the special elements to be on that side as well? Yeah, and it's something you have to watch for. You won't get it in this one because the element by itself will be a metal. Okay, but on occasion you could also get one of those molecular non-metal elements. Okay, so there's the most things to watch for, the most things to be aware of when you're doing a single replacement reaction. Okay, in this case, I have an element that is a metal reacting with the ionic compound. So who is calcium going to replace? Lithium. Okay, they're the ones that have to switch places. So that means that calcium ends up with nitrogen, and lithium ends up by itself. All right, so I got to ask myself, do I have any special elements? The answer to that on this reaction is no, I don't. Okay, lithium's not special. Sorry, lithium. Okay, he's not special. Okay, doesn't need any extra numbers. Okay, calcium nitride is a ionic compound, and it needs to be swapped and dropped. This is a -3, and this is a +2. So I'm going to have Ca3N2 over here. All right, I can start balancing with calcium. It's present in the largest number, or I can start with lithium, okay? But I'm going to start with calcium. All right, there's 3 calcium on that side, so how many do I need over here? 3, okay? And there's 2 nitrogen over there, so what do I need to put here? A 2, okay? And that gives me how many lithium? 6, so what needs to go here? 6, all right? And that's a 1. Okay, everybody all right with that? Okay, making some sense? Okay, now I've got a little flow chart here. I just have to find it. For some reason I couldn't find the file for it. Okay, there it is. Okay, this flow chart right here that I'm going to make a copy of for you. That kind of reminds you of the steps. Okay, you can use it for the first little while you're getting used to predicting equations, but realize that you won't always be allowed to have it. It's not like your periodic table. Okay, this is a crutch, and at some point I'm going to kick that crutch out from under you and make you walk on your own. Everybody with me? Okay, so you can use it at least to get started. So what we look at first here, the first step for all prediction reactions is write out the reactants, because sometimes it's going to be given to you in words, not like it was there. Okay, it'll be given, written out with just the names. All right, swap and drop any ionic compounds and check for special molecular elements. You got to do that in the reactants as well if it's given to you in words. All right, now the next thing is you got to look for what pattern do you have. If you got 2 elements, you're dealing with a synthesis reaction, and we follow these steps. Okay, if it's just 1 compound, okay, then it's a decomp reaction. We follow these steps. Okay, if it's carbon, hydrogen, and oxygen, it's combustion, and we follow these. Okay, single replacement, and you can see here, single replacement has the most steps. Okay, single replacement's got the most things that we've got to look for. Okay, and then double replacement, we simply swap the metals, right? Swap and drop the new ionic compounds, and then balance. Balance is the last step for all of them. Okay, everybody with me on that one? Okay, so I'll make a copy of that for you guys here, and then we'll get going on that. So here's what I want you guys to try for right now. Okay, I want you, let's do 5, 6, and 7 for right now. Okay, so do up to number 7. I'll give you a few minutes to do that while I'm making a copy of that flow chart for you. All right, so for number 5, what kind of reaction have I got going on in number 5? Synthesis reactions, 2 elements, right? Okay, so they're going to go together into a compound. Now, here's a little trick that I sometimes do. I'm giving you this little tip here. Here's a trick I'll do sometimes on a test. Sometimes on a test, instead of writing it the way I wrote it here, I'll write it this way. Why will that give people trouble? Right, you wouldn't believe how many people will then write the ionic compound with the non-metal first, just because that's the way it appeared there. They'll forget, okay, that an ionic compound is always written metal then non-metal, because if I write the product, or sorry, the reactants that way, they'll forget. Okay, it shouldn't make any difference. People should just remember. But I will catch more than half of people if I do that. Okay, so I'm telling you now, do not be in the half that gets caught. All right, telling you my tricks ahead of time, like maybe on a quiz. Okay, so I've got BE with I. Now, for balancing purposes, or sorry, for swap and drop purposes, it's ionic. This is -1. This is +2. So when I swap and drop, I get BE I2. Hey, that's pretty sweet. That one's already balanced. Okay, it's ones in front of everything. Okay, for number 6, I've got potassium reacting with iron 2 oxide. How do I know it's iron 2? Right, there's only one oxygen. Oxygen's -2. Iron has to be +2. Doesn't really matter in this case because iron's going to end up by itself because it's a single replacement reaction. So potassium ends up with oxygen. Iron ends up by itself. Okay, in a single replacement reaction, I need to check for special elements. There aren't any. Okay, then I got to swap and drop ionic compounds. Oxygen is a -2. Okay, potassium's a +1, so we're looking at K2O. Okay, so iron's already balanced, oxygen's already balanced, and now potassium's balanced. Okay, everybody right with that one? Okay. Now, for number 7. Number 7 has a couple of tricks for a double replacement reaction. All right, so I give it away. It's a double replacement reaction. What do I have to do in the double replacement reaction? Switch the metals. All right, so that means copper ends up with chlorine, and magnesium ends up with sulfate. Now, chlorine has more than one possible charge, agreed? Or sorry, copper has more than one possible charge. How do I know which copper it is? Right, it has a -2 charge. So I go back to the reactants, okay, and I look at this. Now, if this was written out with just their names, I would know because there would have been a Roman numeral 2. It would have said copper Roman numeral 2 sulfate. Okay, but in this case, I would have to look and see. All right, copper has a 2+ charge in this one, so it has to have a 2+ charge over here. So we're looking at CuCl2, MgSO4. That's -2. That's +2. So that one's fine. Okay, and it looks to me like everything's already balanced. Okay, everyone all right with that? There's odd situations that may come up. For example, if this, instead of being a double replacement reaction, had been a single replacement reaction, how would I know which copper to use? Because right now, copper's an element, and it doesn't have a charge. And the question wouldn't be able to tell me what charge it has. So how do I know which charge to use? Yeah, I didn't expect you to know the answer. I haven't taught you yet. Okay? The answer is you don't. So, the first charge listed is the most common charge. So you use it. If there's no other way to tell, you go with the most common charge. And for copper, the most common charge is 2. Okay? That doesn't come up very often, but it's still a little trick that you need to remember. Okay? All right, I want you to try 8, 9, and 10. I'm going to go grab your flow charts off the photocopier, okay, and we'll do those when I get back. Okay, so for number 8, carbon hydrogen containing compound reacts with oxygen is combustion. What are the products of combustion reaction always? Water and CO2. Okay, do I have to apply both special balancing rules to this one? Yes, I do. 4 is an even number. Okay, so I apply the rule of 2, and then I balance. 2 times 4 is 8, so an 8 goes there. 2 times 10 is 20. 10 times 2 is 20. Now I balance the oxygens. 8 times 2 is 16, plus 10 more is 26. 13 times 2 is 26. Okay, everybody all right with that one? All right, so like we said, other than balancing, combustion are really the easiest ones for prediction because the products are always the same. Okay, in number 9, I have a single compound, in this case rubidium phosphide, and it's breaking down because it has to be a decomposition reaction with only one reactant. So it's going to break down into rubidium and phosphorus. Okay. My flowchart says in a decomposition reaction I need to check for special elements. Rubidium is not special, phosphorus is, and it comes as a 4. Alright, so we got a 4 there. Okay, now I got to balance. It says always balance the thing present in the largest number, so I'm going to balance the phosphorus first, which means I need a 4 here, which gives me how many rubidium? 12. Alright, so we got 4, 12, 1. Okay, and our last one. I've got lead 4 chloride reacting with cobalt 2 phosphate. Okay, so now I've got to identify the reaction type. What kind of reaction has 2 ionic compounds in it? Double replacement. In a double replacement, I switch the metals. Okay, so lead is going to end up with phosphate. And I'm just going to assume it's going to need brackets. Okay, plus, okay, cobalt is going to end up with chlorine. So I have 2 ionic compounds. What do I have to do with them? Swap and drop. Okay, over here, lead was a 4, so it's a 4 over here as well. So I've got plus 4, and phosphate's a minus 3. Right, so when we drop and swap, we're going to PB3, PO4, 4. Okay, and then cobalt over here, we said was a 2. All right, so it's going to be a plus 2 over here, so that's going to give us CO Cl2. So I'm looking at this and thinking, all right, what should I balance first? There's probably going to be some things that are going to get messed up a little bit in here. So let's look at maybe balancing the phosphates first. It's got the biggest number, 4. Okay, so there's 4 phosphates on that side, but there's only 2 over here. So what do I need to put in front of this? A 2. Okay, when I do that, that gives me how many cobalt? 6. All right, so I'm going to put a 6 here. Now, that's going to give me some trouble. Maybe 6 times 2 is 12. Nope, that should work. What times 4 will give me 12 for chlorine? 3. Okay, does that make my lead work out? Yeah, it does. Okay, so that worked out pretty well there. Now everything is balanced. Agreed? Okay. Is this making some sense? Okay. Really, it's not a whole lot different than what you were doing before. It's just now you have to figure out what the products are. Okay. In the end, after that, it's all the same. It's balance and swap and drop and whatever else. Okay. So I'm going to give you this worksheet here. All right. Now, when you get this worksheet, understand that 6 and 7 are beyond anything I would ever ask you to do on a unit exam or a quiz. Okay? They're just if you're starting to feel cocky about your abilities to balance chemical reactions. All right? Because in this one, remember I said sometimes sometimes a polyatomic ion breaks down. Okay? Like so NH4, it splits in this reaction. Sometimes that happens. These ones are pretty complex in terms of balancing. So you don't necessarily have to do them, but if you want a challenge, feel free. Okay? Okay, so in Science 10 stuff, okay, and go down to the chemistry folder, and I think it's called Keys to Prediction Worksheets. No, sorry. It's under keys to all reaction worksheets. It's in that same key you've been using. Okay. The keys for this one and for the two that I gave you today should also be in that file. All right. Just got to go through it a little ways. Be like page 5 or 6 or something. Okay. So that's where you can find those ones. Okay, guys. For the first two here, where these two metals are added to water, there's actually two possible answers. I don't think I have both on the key. Okay. But just so you see them here. One possibility is K plus HOH. If you wrote it that way, okay, as a single replacement reaction, you get KOH plus H2. Okay, that's one way for that to go, and then of course you'd need a 2 here, a 2 there, and a 2 there. Okay, but there's another way that that could possibly go. You could have written it as K plus H2O. And if that's the case, you end up with that instead. Either way is right. Okay. In reality, both of those happen when you mix potassium with water. Okay. You get a lot of hydrogen gas being produced either way. Okay. But the solution ends up being some K2O and some KOH. Okay. As a result, so either one of those would be correct in the end. Okay, so I would accept either one. Same thing happens with calcium. Okay, you could have Ca plus HOH, and you would end up with H2 plus CaOH2. Okay, and then you need a 2 there. Or you could have Ca plus H2O, okay, which would give you CaO plus H2, and that reaction would already be balanced. And again, either one of those is technically correct because both happen. All right. Does that sort of make sense, everybody? So it doesn't really matter which one you picked. You picked the right one either way. Right? And because in reality, both happen. Okay. Any other ones giving us trouble there? Okay. Keep going then. So the question is, does it matter whether I wrote CaOH first and H2 second? Does it matter? Makes no difference. As long as you have them both there, I don't care which one you wrote first. Okay? If you wrote, so let's say instead of writing it as H2 plus CaOH, you wrote it as CaOH plus H2. Okay? Are you saying the same thing? You're saying my products are calcium hydroxide and hydrogen. It doesn't really matter which one you list first. Okay? As long as they're both there. All right? So no, it doesn't really make any difference which way, which order. Okay, so this sheet's not for homework. All right, we're going to be working on it again tomorrow. Tomorrow's quiz will be very much like Thursday's quiz. It'll have a bunch of reaction stuff and probably one prediction question at the end. Okay, be a lot like that. All right, so that's what you can expect. That'll be posted sometime this afternoon, so you can check it out tonight. Spend some time tonight working on that. All right. Remember, your toxin project is due March 11th. Okay, that's next week on Wednesday, so make sure you're spending a little bit of time tinkering around with that as well. Okay.